Today's lesson is about the very important distributive property. We're going to first talk about algebra tiles. You don't need to make any notes on this on your sheet. You can just watch what we're doing here. We're going to talk about the distributive property, but first I'm going to talk about what it means in terms of a rectangle. So length times width is the area of a rectangle. So I'm going to build a rectangle here, but in the length of my rectangle is going to be 3x plus 1, and the width is going to be a 2. So we're going to talk about how to make this an area kind of question here. So think of an algebra tile, one of those little white, one of the little square beige ones represents 1. And we want a height of 2, and this would be the length of an x. So there's 3 x's, and there's a length of a unit 1. So let's fill it in with all of the tiles. So this area represents 3x plus 1 by 2, multiplied by 2. So when you count up all the tiles that we have here, how many tiles do we have? So 2 times 3x plus 1 is equal to 6x plus 2. So there's 6 of the x ones, and then there's 2 single ones. Let's try 3 times x plus 4. So that would look like this. There's an x, and there's 4 along the bottom, but we've got 3 rows of them. So it's 3 deep of x and then plus 4. So what is 3 times x plus 4? So we count up everything we have here, and 3 times x plus 4 is equal to 3x plus 12, single ones. Let's do another one. What if we had x times 2x plus 1? So this is the first time we've had an x in the front of the bracket instead of a 2 or a 3. How are we going to draw an area, a length, and a width with that? So there's a 2x plus 1, and there's the length x. We fill it all in, and we get x squared this time. Because if we've got one length of x and another length of x, well then that area is going to be an x squared. So x times 2x plus 1 equals 2x squared, that's these two big square ones, plus a single x. One more, let's try one more algebra tile. X times 3x plus 2. There's your 3x plus 2, and there's your x. And now we're going to turn it into an area, a length, and a width, and we fill it all in. So x times 3x plus 2 equals what? What do we have when we count up our tiles? We have 3x squared tiles, and we have 2 x's. Now we're going to move on to your handout here. Remember how to do this. This is the exponent laws, the product law. What would we do here when our bases match? What do we do to the exponents? We add them. That's the product law, so that gives us m to the power of 9. Now let's make it a little harder. What will we do in this case? So look at our m's. Just look at the m's first. This is still an m to the power of 7 like that one was, and this one's still an m squared like that one was. So if we ignored the n's and just looked at the m's are exactly the same as what we had above. So we're going to get this same answer for our m's, but we also have n's here. So we're going to collect the n exponents too. So here's our m's, same as what we did up here, but our n is the 5 and the 2. So we keep the matching letters together. So the m exponents go together and the n exponents go together. That gives us m to the power of 9 times n to the power of 7. Okay, so we're using the product law, and the rule is when your bases match and you're multiplying them, you add the exponents. So the quotient law would be if you were dividing, you would subtract the exponents. So we're just talking about the product law right now. So the only change I've made is we've got it looking a little more complicated. We've got different letters, but we still keep our letters together. And the main rule for today's lesson is that you put matching bases together by adding exponents like we did in that previous example. If we have numbers in the question, they will multiply together, and I'll show you that in a minute. If you have m's, they get multiplied with the m's. If you had n's, they get multiplied with the n's. If you have y's, they get multiplied with the y's, and so on. Now, technically, these should not have apostrophes, right? Because grammatically, this is not possessive. This should just be ms, but I thought if I just wrote ms and ys, that would confuse you. But The exponents don't need to match when you're multiplying. When we're multiplying, it's not the same as collecting like terms. If I were collecting like terms here and I had m to the power of 7 plus m to the power of 2, I can't add those. They are not like terms. I can't add them. But I can multiply them. So if that weren't addition but it were multiplication, that's fine. If that's multiplication, that's the top question we just did on the top of the screen, m to 7 plus 2. When we're multiplying, the exponents don't need to match, but they must match if you are adding. Or they wouldn't be like terms otherwise. Simplify the following using the product rule. So we've got 3 examples we're going to do here. Let's look at the first one. 12a cubed times 7a to the power of 5. So look at our rule up here, numbers times numbers. So I'm going to do the 12 and the 7 first. I'm multiplying, so I'm going to just multiply the 12 with the 7. That's going to be my first step here. That's an 84. Now I do a's times a's. So a cubed times a to the power of 5. That's your product law. You already know that one. We're going to add the exponents, and that's going to give us a to the power of 3 plus 5. And when we put it all together, we have 84 a to the power of 8. So maybe now's a good time to press pause and try this one. See if you can do this one, and then I'll show you right here. Okay, first thing we're going to do is numbers times numbers, coefficients times coefficients. So that's a negative 5 times a 2. I'm going to multiply those together first. That gives me a negative 10. Now I'm going to do my letters, x's times x's. Remember, the exponents don't need to match. I can multiply x squared times x. I can't add them together, but I can multiply them together using the product law. So my final answer will be negative 10x cubed. If you did that one on your own and you didn't get that answer, hopefully my explanation helped you to understand where you went wrong. This one's a little bit different, but we're still following this rule. Numbers times numbers. So I have 3 numbers. I have a 2 and a negative 3 and a 5. When I multiply those together, I get a negative 30. Now I'm going to go to my letters. Here's an A. Now that's an A to the power of 1. There's no A here, so I can't, doesn't matter, it doesn't change my answer. But I have an A to the power of 1 and I have an A to the power of 3. So those I add together and my answer is negative 30a to the power of 4. So we only have one more slide after this one. Here's some notation. Whether I write 3b like that right beside each other, or 3 times b, or 3 with a dot b, or in brackets, or with just part of it in brackets, they're all ways of saying the same thing. They're all 3 times b. They're all, whatever your b is, it's a variable. I don't know what b is supposed to be, but I'm multiplying that by 3. Example 2, expand using the distributive property. So here we're getting into the whole title of today's lesson. Definition: expand means multiply it all out. It means expand it all out. So we talked about the distributive property in a previous lesson. We've distributed. So let me change to a pen here. M times 2m. So the m is touching the bracket. So the m has to get distributed into the bracket with multiplication. So it first gets, we've done this before, but with just a plus or a minus. Now we're bringing an m in. So now I have to do m times 2m. What's m times 2m? Well, remember, numbers with numbers. There's an invisible 1 in front of that m. So 1 times 2, I get a 2. That's the first thing I'm going to get, is a 2. Now I do letters times letters, m times m. That's going to give me an m1 plus 1, m squared. Now, I'm going to switch colors. I'm going to take this m and I'm going to multiply it. I'm going to distribute it over to the 1. Now, anything times 1 is easy because when you multiply by 1, you just get your original piece back. So I'm just going to put plus m here. So when I put it all together, I'm having a hard time there, with that, m, okay? When I put it all together, I get an answer of 2m to the power of 2 plus m. It's very tempting to want to add these together here. Oh, they look so, could I not make this 3m squared or something? No, I can't make it 3m squared. because these are not like terms. M squared, let me erase this, M squared is maybe this shape. Remember what a squared shape looks like? Maybe that's an M squared, and maybe I have two of those, two M squareds like that. An M, however, is just a single rectangle. That would be an M. So I can't add those together and get 3M squared. I don't have 3M squareds. I only have 2M squareds here. I can't add them together and get 3M cubed or something like that. I don't have a cube shape here, right? A cube shape would be like this. It would be 3 dimensions. It's kind of hard to see what I'm drawing here, but that's supposed to be a cube. That would be an M cubed. I don't have an M cubed, so I cannot add those two together. Let's look at the next one. 6a squared minus 5 times 2a. So again, we have to distribute. We're going to distribute this into this bracket, and this time we have two things to bring in. Then we have to bring in the -5, but one thing at a time. Let's do 6a squared times 2a. Numbers times numbers, so 6 times 2, we'll do that first, that gives me a 12. And then the a squared times the a, so a squared times a, for my product law, I know that'll be a to the power of 3. Now let's do the next part. Now I take the -5, and I have to distribute that into this bracket. Let me erase some of the blue here, so you can see. -5 times 2a, okay, numbers times numbers, so that's -5 times 2, that's going to be a -10, and then letters times letters. I have an a here, I don't have an a in my first piece, so I just have a single a. My answer there is 12a cubed minus 10a, and those are not like terms. I cannot put those together. A cubed and a are not the same. They're different shapes. We've got a cube, and then we've got a single rectangular stick kind of thing. They're not the same. You cannot add those, so that's done. Students get confused here a lot because we can multiply unlike terms together. I'll put this up at the top here. If I had 12a cubed times -10a, I could do that. That would give me -120 a to the power of 3 plus 1 a to the power of 4. I can multiply that. Multiplying is always easier. I can multiply anything. Just like with fractions, if I had 1/2 times 1/3, no problem, that's 1/6. But change that to a plus, well, now I need a common denominator and I have to change things because they don't match. So that's a lot harder. So that wouldn't be 1/6. Multiplying is always easier. So we're multiplying these ones and we cannot add them together. Down to b down here, I can't add those two. They're not like terms. But I could multiply up here, because multiplying, we can multiply whatever we want together. Okay, let's go to part C. This one's even more complicated. So the -4, let's start with that. That's touching the bracket. That has to come in with multiplication to both of these terms. And then the bracket stops it, right? The bracket stops that -4 from going any further. So -4 times 2p. What's -4 times 2p? First of all, numbers times numbers. -4 times -2 is times +2 is -8. And then I only have a single p. So that's just one p there. Now we'll go on to the next piece of that. That's the -4 times 1. -4 times 1, again, when we have a 1, it's great. We don't have to think too much. That's just going to be a -4. Now we have, we're starting a new section here. We've got a -3, and we've got to take this -3, and it's touching this bracket, so I have to distribute it in right up until the end of the bracket. The -3 has to go into each of the 3 parts of this trinomial. -3 times p squared, let's do that first. -3 times p squared is simply -3p squared, because we only have one number to multiply and we only have one letter to multiply. Next one's a little harder. We've got -3 times 4p, So numbers times numbers, negative 3 times 4, that's going to give me a negative 12. And then I only have the one p there. I don't have another one, so it's going to stay p. I don't have another one with the negative 3. And then the last one is negative 3 times negative 1. That's positive 3. Okay, look at what I've got here. Now I have some like terms. I haven't had any like terms before, but I do now. Remember, we always start with the highest power first. So I'm going to start first with the p squared. That's the highest power. It takes precedence. It gets to go first. So I've got a negative 3p squared. Do I have any other p squareds? No. Okay. Now let's move on to the p. I've got this negative 8p here. And do I have any other single p's? Well, p to the power of 1. Yeah, I got one right here. Negative 12p. Those are like terms. I'm going to collect those. Now let's go to the constants. I have a negative 4 right here. Negative 4, that's a constant. And I have a positive 3, that's a constant. So those go together. My final answer, let me put it in red. My final answer is going to be negative 3p squared. It's the only p squared that's there. These two go together. Negative 20p. And these two go together. Negative 1. So that last one is the most complicated one that you've had. I would recommend you do it again. You back up the video a little bit, a few minutes, and you try it again. Maybe flip your sheet over and just do it on the back. See if you can do it. It's tricky because it has several pieces to it. And then you have to collect like terms after it. So that's a good one to try. And then when you're done, on the bottom of your handout, it tells you what questions you need to do from your textbook. So do lots of practice. This is a really important concept, the distributive property. We've already been talking about it. We're going to do it again. Our next lesson is distributive property again. So you've got to understand it today because we're going to keep building on it. Well, good luck with your work, and let me know if you have any questions.